The shocking truth about fasting and cancer. What science really shows, not what doctors say. In 2016, a significant study was published in JAMA Oncology, a highly respected medical journal focused on cancer research. This research involved tracking over 2,400 women who had been diagnosed with early-stage breast cancer. These women were observed for more than 7 years, and their backgrounds varied widely in terms of age, previous treatments, and lifestyle choices. When the researchers meticulously analyzed the collected data, a striking pattern emerged concerning who was more likely to experience a recurrence of their cancer. Surprisingly, it wasn't a specific medication or a genetic marker that stood out as the strongest predictor. Instead, it was an eating pattern. The findings indicated that women who consistently fasted for fewer than 13 hours overnight had a significantly higher risk, 36% more, of their breast cancer returning compared to those who fasted for 13 hours or longer. It's important to note that the average age of the women in this study was 52. This 36% increase in risk was directly linked to the duration of their overnight eating break. What is about to be shared is not considered fringe or unconventional science. The information is supported by research published in well-regarded journals such as JAMA Oncology, Science Translational Medicine, Cell, and Nature Communications. Furthermore, this research is often funded by prestigious institutions like the National Cancer Institute. The scientific exploration into fasting and its effects on cancer is being conducted by leading oncologists, immunologists, and molecular biologists from prominent research institutions globally. The existing knowledge gap is not about what medical professionals are deliberately withholding. Rather, it lies in the difference between the rapidly emerging scientific findings and what has been studied extensively enough and with a large enough patient population to be formally adopted as clinical recommendations. Understanding this distinction is crucial, as it highlights that the evidence being presented is genuinely exciting without any implication of secrecy. Today, we will delve into 5 distinct biological mechanisms through which fasting appears to influence the development and progression of cancer. You will be presented with actual studies, specific data points, and a clear understanding of the limitations of the current evidence. Following this, you will receive a practical approach rated by the effort and potential risks involved that individuals over the age of 50 can begin to implement based on the current scientific understanding. At the conclusion, you will also be informed about the areas where the research still holds significant uncertainty, as this is just as important as knowing what has been established. If you find this in-depth research valuable, your subscription is a great way to support its continuation. There's no obligation, but it signals that this is a topic worth further exploration. Let's start by revisiting the study that was initially mentioned to ensure a thorough understanding before moving on to the underlying mechanisms. The research paper published in JAMA Oncology by Marin and her colleagues was part of a larger initiative called the Women's Healthy Eating and Living Study. The participants in this study were women who had already received a diagnosis of early-stage breast cancer, specifically stages 1 through 3, and were being closely monitored for any signs of the cancer returning. The primary focus of the researchers was not explicitly on fasting itself. Instead, they were examining data that participants provided about their eating habits, known as dietary recall. During this analysis, they observed that the duration of the overnight fasting period, the time between consuming the last calorie in the evening and the first calorie in the morning, varied considerably among the women. Some participants finished their evening meals as early as 6 p.m. and didn't eat again until 8 a.m. the next day. Others continued to snack until 10 p.m. or even 11 p.m. and then had their breakfast at 7 a.m. This resulted in a difference of approximately 5 to 6 hours in their overnight fasting periods between these two groups. The significant finding was that women who fasted for less than 13 hours were associated with a 36% increased hazard ratio for breast cancer recurrence. This statistic remained even after accounting for various other factors that could influence cancer recurrence, such as overall calorie intake, physical activity levels, alcohol consumption, and the duration of sleep. The study also noted that for every additional 2-hour increase in overnight fasting duration, there was a corresponding decrease in HbA1c, which is a measure of average blood sugar over 3 months, and an improvement in sleep quality. These associations remained statistically significant when subjected to multivariate analysis, meaning the findings were not likely due to chance. However, it is crucial to present an honest and important caveat regarding this study. While compelling, it is not definitive proof. The study design was observational, meaning it observed existing behaviors and outcomes. It is possible that the length of the overnight fast is not the direct cause of the observed outcome, but rather a marker or proxy for a cluster of other healthy behaviors. For instance, women who fasted longer might also tend to go to bed earlier, consume less alcohol in the evenings, and generally have better sleep hygiene. The researchers could not definitively prove that fasting itself was the driver of the outcome, as opposed to these correlated healthy habits. The findings for recurrence-free survival were statistically significant, but the findings for overall survival were not. This distinction is important because it suggests that there is likely real biological influence on cancer behavior. However, the full implications of this biology for long-term mortality are still being investigated. Essentially, this study opened a door, and over the past decade, a substantial amount of mechanistic and clinical research has been built upon that initial observation. A subsequent important area of research stems from the laboratory of Dr. Walter Longo at USC, and it involves a randomized controlled trial that many consider to be among the most interesting dietary intervention studies of the last decade. Published in Science Translational Medicine in 2017, this trial involved 100 generally healthy adult participants. They were randomly assigned to one of 2 groups: either undergo 3 cycles of what Dr. Longo terms the fasting mimicking diet, FMD, for 5 days each month, or follow a normal, unrestricted diet as a control group. The fasting mimicking diet involves consuming a very low-calorie, plant-based diet that is low in protein and high in fat. On the first day, participants consumed around 800 calories, and on days 2 through 5, the calorie intake dropped to about 500 calories. Out of the participants, 71 completed all 3 cycles of the diet. The results observed across various biomarkers were quite remarkable. There was a noticeable decrease in body weight. Both trunk fat and total body fat were reduced. Blood pressure also decreased. Insulin resistance, measured by a metric called HOMA-IR, improved by 20%. Most significantly, in relation to cancer risk, IGF-1, insulin-like growth factor 1, which is a key hormonal driver of cell proliferation, declined significantly. This effect was most pronounced in participants who initially had IGF-1 levels above 225 nanograms per milliliter, which is precisely the group considered to be at the highest risk for cancer. A further analysis conducted in 2024, focusing on 15 participants from that same trial and published in Nature Communications, took the research a step further. This analysis utilized validated biological age models, including the Grimmage and PhenoAge epigenetic clocks, which are now recognized as highly reliable indicators of morbidity and mortality. The researchers discovered that completing 3 cycles of the fasting mimicking diet was associated with a 2.5-year reduction in median biological age, and this reduction was independent of any weight loss. This means participants became biologically younger by 2.5 years as a result of 3 5-day dietary interventions spread over 3 months. It is important to exercise caution and avoid overstating this particular finding. The sample size of this secondary analysis was only 15 individuals. Additionally, the commercial fasting mimicking diet product Prolon is sold by a company in which Dr. Longo has a financial stake, which is a potential conflict of interest that must be considered when interpreting his research. Furthermore, while biological age clocks are increasingly validated, they are not perfect predictors of individual health outcomes. What can be confidently stated is that the direction of these findings is consistent across multiple measurements and various studies. The underlying biological mechanisms are now well understood. providing a clear rationale for why these changes might be occurring. The third piece of evidence we will consider comes from a systematic review published in Nutrition Reviews in 2024. In this review, researchers examined nearly 14,000 study results and narrowed them down to 24 studies specifically looking at time-restricted eating, TRE, in individuals who had already been diagnosed with cancer, some of whom were undergoing active treatment. A key finding was the high adherence to fasting protocols. Between 67% and 98% of participants in various studies managed to stick to their designated eating windows. This is a significant number, as it suggests that if fasting were prohibitively difficult for individuals dealing with cancer, adherence rates would likely be much lower. The data from these studies, when they measured cancer-relevant markers, showed reductions in CEA, carcinoembryonic antigen, a type of tumor marker, and in some populations, reduced recurrence rates. Consistently, improvements were observed in BMI, blood sugar regulation, and inflammatory markers within as little as 8 weeks. It is also noteworthy that the National Cancer Institute funded 5 intermittent fasting studies in 2020, with 4 of them focusing specifically on time-restricted eating. This indicates that the federal agency responsible for cancer research is actively investing in understanding this area, which is a clear signal of its mainstream scientific prioritization, not a fringe pursuit. Now let's delve into what is actually happening within the body, as this is where the story becomes truly remarkable. Once the patterns in these studies became clear, it was imperative to understand the underlying mechanisms. What is it about fasting that has the potential to alter cancer behavior? The answer lies in 5 interconnected biological processes, and none of them are immediately obvious without closer examination. The first mechanism can be thought of as starving the engine. Cancer cells possess a characteristic that scientists identified decades ago, but its full clinical significance has taken time to be appreciated. In 1924, Otto Warburg documented what is now known as the Warburg effect. Cancer cells exhibit an exceptionally high rate of glucose metabolism, even when oxygen is readily available. They generate energy through a process called glycolysis, rather than the more efficient oxidative phosphorylation preferred by normal cells. This means that cancer cells are heavily reliant on a constant and ample supply of glucose. They have essentially rewired their metabolic systems to demand continuous, high-volume fuel delivery. The problem with this rewiring, and what makes fasting mechanistically so interesting, is that it creates a lack of flexibility. Normal cells, according to metabolic biologists, possess metabolic flexibility. This is their ability to switch between different fuel sources depending on what is available. When glucose levels are low, healthy cells can shift to burning fat and producing ketone bodies, which their mitochondria can then utilize efficiently. When glucose becomes available again, they switch back. Your brain, heart muscle, and liver are all capable of this adaptation. In most cases, cancer cells have lost this flexibility. The same mutations that drive their uncontrolled proliferation, such as those in genes like RAS and PI3K, also lock them into a dependency on glycolysis. They struggle to use ketones and cannot easily downregulate their metabolic rate when the fuel supply decreases. Consequently, when you fast, causing blood glucose and insulin levels to drop, your normal cells adapt and thrive. However, many cancer cells, particularly those exhibiting the most aggressive growth patterns, experience significant metabolic stress. This leads to the generation of excess reactive oxygen species, accumulation of DNA damage, and an increased vulnerability to apoptosis, the process of programmed cell death that they typically evade. Think of it this way: your healthy cells are like hybrid cars. They run on gasoline when it's plentiful and switch to battery power when it's not. Cancer cells, on the other hand, are like old-fashioned, gas-guzzling engines that can only run on gasoline and require a constant supply. Fasting effectively changes the fuel environment. The hybrid vehicles can adapt to the new conditions, but the old engines can stall when they can't get the fuel they need. This is the first critical mechanism, but it doesn't operate in isolation. The second process is something that most individuals over 50 may not have encountered, despite it being one of the body's most vital protective mechanisms and one of the first to decline with age. This process is called autophagy. Derived from Greek words meaning self-eating, autophagy is essentially the cell's internal maintenance and recycling program. When cells experience a shortage of nutrients or metabolic stress, they activate a process where they literally break down and recycle their own damaged components. This includes damaged mitochondria, misfolded proteins, dysfunctional organelles, and any cellular debris that has accumulated over time. Within the cell, specialized compartments called lysosomes form structures called autophagosomes around this damaged material. They then break it down into its basic components, which can be reused for energy or rebuilt into functional proteins. The pathway for activating autophagy is relatively straightforward in its outline, even though the molecular details are complex. Fasting activates a key cellular energy sensor called AMPK, AMP-activated protein kinase. AMPK signals low energy levels when the ratio of ATP to AMP drops. Activated AMPK then inhibits mTORC1, mammalian target of rapamycin complex 1, which is the primary brake on autophagy. With this brake released, another protein complex called ULK1 is activated, initiating the autophagic process. The timing of this process is important. In humans, significant induction of autophagy in metabolically active tissues typically begins after approximately 12 to 16 hours of fasting. Here's how this directly relates to cancer prevention. Precancerous cells, cells that have accumulated DNA damage and early cancerous mutations but haven't fully transformed, often generate abnormal proteins and dysfunctional mitochondria as a consequence of this damage. In cells with intact autophagy, these damaged components are cleared out before they can contribute further to cellular dysfunction. Imagine autophagy as the maintenance crew of a building. Every day they come through, fix what's broken, and remove the debris, keeping the building in good working order. Now, picture what happens if that maintenance crew stops showing up. If you go months or years without clearing the accumulating damage, the building deteriorates in compounding ways. After the age of 50, the activity of autophagy measurably declines. This decline is linked to age-related reductions in AMPK sensitivity, an increase in basal mTORC1 activity possibly due to chronic low-grade inflammation, and epigenetic silencing of genes that are crucial for autophagy. The consequence is that cellular maintenance functions less frequently and less effectively, precisely at a time when cells have had the most opportunity to accumulate damage. Fasting, however, reliably restores autophagy signaling. A 2024 review in Aging Research Reviews documented that fasting-induced autophagy is one of the most consistent interventions for reversing age-related declines in cellular maintenance. Animal studies have demonstrated that stimulating autophagy through fasting or compounds like rapamycin can extend average lifespan by up to 17%. While we don't have equivalent human longevity data yet, as such studies would take decades to complete, the mechanistic case is very compelling. The third mechanism is perhaps stranger and more counterintuitive than the first two. Dr. Longo's laboratory has termed it differential stress resistance. Once you grasp this concept, the implications for both cancer prevention and cancer treatment become considerably more significant. The fundamental idea is this: when a cell senses that it is deprived of nutrients, it has two potential responses. If the cell's growth-regulating systems are functioning correctly, meaning the genes that govern cellular behavior are operating normally, the cell enters a protected state of low activity. It reduces growth signals, activates stress resistance pathways, decreases its metabolic demands, and becomes more resilient to damage from oxidative stress, chemotherapy, and other cellular insults. Normal cells accomplish this efficiently because the pathway from nutrient sensing to growth suppression, primarily through IGF-1 reduction, PI3K pathway downregulation, and FOX transcription factor activation, is intact. However, cancer cells cannot do this. The same oncogenic mutations that drive their rapid proliferation, such as activated RAS, constitutively active PI3K, or loss of PTN, keep the growth signaling pathway permanently switched on, regardless of nutrient availability. The cancer cell receives the signal that nutrients are scarce, but it is unable to respond appropriately. It cannot slow down, cannot activate protective pathways, and cannot reduce its metabolic rate. It continues to operate at full speed, even as the environment becomes more challenging. The clinical implication that Dr. Longo and his colleagues have been investigating is whether fasting before and during chemotherapy can create a situation where normal tissues are protected by entering this stress-resistant state, while cancer cells remain fully vulnerable to the toxic effects of the drugs. A small pilot study conducted in female cancer patients indicated that fasting for 48 hours prior to chemotherapy was associated with a reduction in hematological toxicity, meaning less severe drops in white blood cells and platelets. Another direct trial in breast cancer patients, which tested a 5-day fasting mimicking diet combined with neoadjuvant chemotherapy, did not find a significant difference in its primary endpoint related to side effects. However, in a per-protocol analysis, the group that followed the FMD showed a 4-fold higher likelihood of achieving a pathological complete response, which signifies a complete or near-complete disappearance of tumor cells at the time of surgery. This is a striking secondary finding that warrants replication in larger trials. It is important to be precise about the current standing of the evidence. The data from animal studies supporting differential stress resistance is robust. The human data, while promising, is based on small sample sizes. Major cancer organizations like the American Cancer Society and MD Anderson currently advise against fasting during active cancer treatment outside of clinical trial settings. This guidance is in place for good reasons, not because the underlying biological mechanism is implausible, but because large-scale, randomized controlled trials are still needed to definitively determine who benefits, who might be harmed, and what the optimal fasting protocols are for healthy adults aiming for cancer prevention, which is the primary focus of this discussion. The risk assessment for cancer prevention is quite different from using fasting during active treatment. The fourth mechanism is hormonal and involves a number that more individuals over 50 should be aware of: IGF-1, or insulin-like growth factor 1. This hormone is primarily produced by the liver in response to growth hormone signaling and dietary protein intake. Its role is to stimulate cell growth, cell division, and cell survival, and it actively inhibits apoptosis, the programmed cell death that normally clears away damaged or abnormal cells. While IGF-1 is essential in appropriate amounts and at certain life stages, chronically elevated levels, particularly in adults over 50 who are no longer in their growth phases, have been consistently linked to an increased risk of breast cancer, prostate cancer, colorectal cancer, and lung cancer. In 2014, a landmark paper published in Cell Metabolism by Levine and colleagues analyzed data from the NHANEAS 3 study, a nationally representative sample of American adults. They found that high animal protein intake in adults aged 50 to 65 was associated with a 74% increase in cancer mortality and a 4-fold increase in the risk of dying from cancer. The authors specifically identified IGF-1 as the primary mediator of this effect. High protein consumption stimulates IGF-1 production, and elevated IGF-1 promotes cell proliferation and survival throughout tissues, including cells that may have early oncogenic mutations but would otherwise die. The same study also found that after the age of 65, this relationship inverted, with low protein intake in that age group being associated with increased mortality. This is a critical nuance for anyone listening. The relationship between protein, IGF-1, and cancer risk appears to be particularly concentrated in the 50 to 65 age window. After 65, adequate protein becomes even more important, not less, as sarcopenia, the age-related loss of muscle mass, emerges as a dominant health risk. Fasting offers a means to periodically lower IGF-1 and reset that hormonal environment without requiring a chronic restriction of the protein that aging muscles need for maintenance. The Longo Fasting Mimicking Diet (FMD) protocol is specifically designed around this biological principle. The 5-day cycles are intentionally low in protein to drive IGF-1 down, The period of refeeding between cycles is when protein intake returns to normal levels to support muscle maintenance. The oscillation between these states, rather than permanent restriction, is the intended intervention. The fifth mechanism involves immune system reprogramming. This is a crucial piece that connects the research on the gut microbiome, which has been discussed in other contexts, with the cancer biology we are exploring today. Your immune system is designed to function as a continuous surveillance network, identifying cells that have accumulated dangerous mutations and eliminating them before they can develop into clinically detectable tumors. This process, known as immune surveillance, is not perfect, but is critically important. Individuals who are immunocompromised for any reason experience dramatically higher rates of cancer across virtually all cancer types. After the age of 50, the immune system undergoes aging, a process called immunosenescence. A key change that occurs is an imbalance between lymphoid cells and myeloid cells. Lymphoid cells include your T cells and natural killer cells, which are the active attackers that identify and kill cancer cells. Myeloid cells, such as monocytes, macrophages, and dendritic cells, are also critical for immune function. However, in states of chronic inflammation, the myeloid compartment can become dominated by cells that suppress anti-tumor immune responses rather than promote them. Chronic low-grade inflammation, which is almost universal in adults over 50 consuming Western diets, shifts the immune balance towards this myeloid-dominant, pro-inflammatory, and cancer-permissive profile. The 2024 Nature Communications analysis of the Longo FMD trial revealed that 3 monthly 5-day fasting cycles increased the lymphoid to myeloid ratio, effectively shifting the immune profile back towards a younger, more surveillance-competent state. Separate research by Dubiak and colleagues demonstrated that fasting alters the expression of HO1, hemioxygenase 1, a protein, in opposite ways in normal cells versus cancer cells. In normal cells, fasting increases HO1, making them more resistant to immune attack and chemotherapy. Conversely, in cancer cells, it decreases HO1, making them more vulnerable to CD8+ cytotoxic T cells. This differential modulation of HO1 is one of the most elegant biological mechanisms encountered in this field, as it creates conditions that simultaneously protect what should be protected and expose what should be eliminated. None of these 5 mechanisms operate in isolation. They function as an integrated system. When you fast, insulin levels drop, blood glucose falls, IGF-1 declines, autophagy becomes activated, and the immune balance shifts. You are not just doing one thing to cancer, you are fundamentally altering the entire biochemical environment in which cancer cells must operate. This environment becomes less conducive to growth. Immune surveillance becomes more effective. Cellular maintenance, which prevents the accumulation of damage that leads to cancerous transformation, becomes more active. Now, let's consider how to apply this information. The most critical takeaway before discussing a protocol is this: the evidence base for fasting and cancer prevention is at different stages of development depending on the specific question being asked. The evidence that simple dietary modifications, particularly extending the overnight fast, correlate with a reduced risk of cancer recurrence is based on human observational data from a large, well-designed study. The evidence that the fasting-mimicking diet can reduce IGF-1, insulin resistance, inflammatory markers, and biological age markers comes from a randomized controlled trial. The evidence that these changes might reduce cancer initiation risk in healthy adults over long periods is mechanistically compelling, but has not yet been definitively proven through prospective, long-term human trials. It is important to hold all 3 levels of certainty in mind as we proceed. Priority 1 is the 13-hour overnight fast. This is what the JAMA Oncology study documented. Aim to finish eating by 7 or 8 in the evening, and do not consume any calories again until 8 or 9 in the morning. This should be considered your minimum threshold. It is free to implement, requires no special foods, and does not significantly restrict what you eat, only when you eat it. If you currently snack around 10 p.m. and eat breakfast at 7 a.m., you are fasting for approximately 9 hours. To reach 13 hours, you would need to stop eating in the evening about 4 hours earlier. For most individuals, this means finishing dinner by 7 p.m. and considering the kitchen closed for the night. The biological significance of this is that the metabolic switch, the transition from glucose-based to ketone-based metabolism, begins to occur around 12 to 16 hours of fasting in most adults. At 13 hours, you are approaching the threshold where insulin levels have dropped significantly, liver glycogen stores are being depleted, and the mobilization of fat for ketone production is initiating. You are also entering the window where autophagy induction in metabolically active tissues becomes meaningful. While 13 hours does not induce deep ketosis or represent a dramatic metabolic event, it does reach the threshold where the biological machinery that connects fasting to cancer-relevant processes begins to activate. The most common pitfall observed with this intervention is the late-night snack that people often don't consider eating: a handful of almonds, a glass of milk, or a small bowl of cereal before bed. All of these actions can restart the metabolic clock. It is important to remember that water, black coffee, and plain herbal teas are generally permissible during the fasting window. Priority 2 is to consider moving towards a 16-hour daily fast, if your health allows it. This aligns with the standard 16.8 time-restricted eating protocol, where you eat within an 8-hour window and fast for 16 hours. At 16 hours, the metabolic switch is more fully and consistently engaged than at 13 hours. Autophagy induction is more robust, and IGF-1 suppression during the fasting period is more pronounced. For most individuals over 50, the most practical implementation that works well is to skip breakfast or significantly delay it and eat within a window of approximately 11 a.m. to 7 p.m. or noon to 8 p.m. This approach aligns the eating window with more typical social meal times while still achieving a 16-hour fast from the previous evening's last meal. Some people prefer an earlier window, such as 8 a.m. to 4 p.m., especially if they have a vigorous early morning exercise routine. Biologically, the specific window chosen is less important than consistently maintaining a 16-hour fast. Regarding the evidence for this duration, most time-restricted eating studies conducted with cancer patients utilized fasting protocols ranging from 12 to 16 hours. The optimal duration specifically for cancer prevention has not yet been definitively established through long-term human trials. What is known is that longer fasting periods activate the relevant biological mechanisms more completely. What remains unclear is whether there is a point of diminishing returns, meaning whether fasting for 18 or 20 hours offers significantly more benefit than 16 hours for prevention purposes. The majority of current evidence suggests that 16 hours is where substantial mechanistic activation is achieved without the potential difficulty of longer fasting periods. Priority 3 is the fasting mimicking diet, FMD. This involves 5 days per month of a very low-calorie, plant-based diet. This intervention has the most extensive evidence supporting its impact on cancer-relevant biological markers, but it also requires the most planning and discipline. To be specific about the protocol, on day 1, you consume approximately 800 to 1,000 calories. The composition of these calories is important. High in healthy fats, like olive oil, avocados, and a small amount of nuts. Very low in protein, very low in sugar and refined carbohydrates, and free of animal products. Meals might include vegetable soup with olive oil, a small portion of olives, herbal teas, and water. On days 2 through 5, the calorie intake drops to approximately 500 calories per day, maintaining the same macronutrient composition. Day 6 is a refeeding day, where you gradually reintroduce food, starting with easily digestible items before returning to your normal eating patterns. A commercially available version of this diet is Prolon, which consists of prepackaged foods designed to meet these specific macronutrient ratios. While expensive, it simplifies the planning process. The same protocol can be replicated using whole foods if you are willing to meticulously track your macronutrient intake. The biological changes documented across 3 monthly cycles of the FMD include a reduction in IGF-1, most notably in individuals who started with elevated levels, a 20% improvement in insulin resistance scores, a reduction in visceral and liver fat measurable by MRI, an improvement in the lymphoid to myeloid ratio towards a younger immune profile, and, as mentioned in the secondary analysis, a 2.5-year reduction in median biological age. 3 cycles spanning 3 months represent the minimum duration studied in the randomized controlled trial. Dr. Longo's current clinical recommendation for generally healthy adults is 1 cycle every 3 months for maintenance or monthly cycles for individuals with elevated metabolic risk factors. It is important to address the protein aspect of this protocol, especially considering its significance for the 50 to 70 age range. The data from cell metabolism, which showed a 4-fold increase in cancer mortality associated with high protein intake, specifically focused on adults aged 50 to 65. After the age of 65, the relationship was observed to invert, with low protein intake being linked to higher mortality from various causes. Practically, this means that the protein restriction during FMD cycles, which is key for suppressing IGF-1, needs to be carefully balanced with adequate protein intake during the refeeding periods to preserve muscle mass. For adults in their 50s and early 60s, the periodic low-protein FMD cycles appear to offer benefits in reducing cancer risk. For individuals in their late 60s and 70s, the calculus shifts, and ensuring sufficient protein intake for muscle preservation becomes more critical. The evidence supports an oscillation between restriction and adequacy, not chronic restriction, as the beneficial strategy. Now let's discuss what is not supported by evidence in this field, as it can attract a significant amount of noise alongside the valuable scientific signals. Long-term, severe caloric restriction, essentially chronic semi-starvation, is not supported by the evidence for cancer prevention. Furthermore, it carries genuine risks for older adults, including muscle loss, reduced bone density, nutritional deficiencies, and immune suppression due to inadequate protein intake. The evidence points towards periodic cycling of restriction, not continuous deprivation. Commercially marketed detox fasting programs that claim cancer benefits lack any peer-reviewed scientific evidence. The mechanisms described in this video operate through specific, well-characterized biological pathways like IGF-1 reduction, autophagy induction, and immune remodeling, not through the scientifically unsupported concept of toxin elimination. Multi-day water fasts extending beyond 3 days, when conducted outside of medical supervision, are not supported by current cancer prevention evidence and carry genuine risks, including cardiac arrhythmias from electrolyte imbalances, refeeding syndrome when returning to eating, and orthostatic hypotension, a sudden drop in blood pressure upon standing. The 5-day FMD protocol, by keeping calories low but not zero and with a specific macronutrient composition, is designed to minimize these risks. The evidence for prolonged dry fasting, where both food and water are avoided for any health benefit, is essentially non-existent, and this practice is dangerous. Let's outline the timeline of what you might expect if you begin implementing these strategies. In the first 1 to 2 weeks of transitioning to a 13 to 16-hour eating window, the primary adaptation you will likely experience is related to hunger signaling. Most individuals accustomed to eating across a 12 to 14-hour day may notice increased hunger in the mid-morning, around the time they would typically have breakfast, or in the late evening. This is a ghrelin adaptation. The hunger hormone is cycling according to your previous meal timings and typically takes 2 to 3 weeks to reset to your new schedule. It is important to push through this initial phase. By the end of the second week, morning hunger typically subsides as ghrelin adapts. Some individuals may experience initial fatigue, mild headaches, or difficulty concentrating during the first week. These are common side effects and generally resolve within 7 to 10 days as the body adjusts to the metabolic shift. By the end of the first month, if your baseline fasting glucose or HbA1c levels were elevated, you will likely see early improvements. Inflammatory markers like HS-CRP, high-sensitivity C-reactive protein typically begin to decline within 4 to 8 weeks of consistent time-restricted eating in individuals who started with elevated levels. If you undertake your first FMD cycle within the first month, expect fatigue and headaches, most prominently on days 2 and 3, which are typically the glycogen depletion phase. Most people find days 4 and 5 to be easier as ketone production increases, and mental clarity often returns or even improves. After 3 FMD cycles, approximately 3 months of monthly practice, studies show a measurable reduction in IGF-1 in those who started with elevated levels, an improvement in HOMA-IR, and changes in body composition towards reduced fat mass with preserved lean mass, provided protein intake was adequate during refeeding periods. The finding of a reduction in biological age was observed at this 3-cycle mark. For those who wish to seriously monitor these changes, the key markers to track would include fasting IGF-1, available through standard lab panels, fasting insulin, HOMA-IR, calculated from fasting glucose and insulin, HSCRP as an inflammatory marker, and HbA1c, taking a baseline measurement before starting. And repeating these measurements after 3 months of consistent practice will provide a meaningful before and after comparison. Before concluding, it is essential to explicitly address safety parameters. The fasting mimicking diet or extended fasting protocols should not be attempted by individuals with type 1 diabetes, as the risk of severe hypoglycemia is significant and cannot be managed without medical supervision. The same caution applies to individuals with type 2 diabetes who are managed with insulin or sulfonylurea medications such as glipizide, glyburide, or glipizide. These medications can lead to dangerously low blood sugar levels during fasting. Management with metformin alone presents a different situation with a lower risk of hypoglycemia, but it is still advisable to discuss any fasting protocol with your physician beforehand. If you are currently undergoing chemotherapy or radiation therapy for any cancer diagnosis, do not introduce a fasting protocol without the explicit knowledge and approval of your oncologist. While the evidence for fasting during active treatment is promising, it is not yet sufficient to be implemented outside of clinical trial settings or direct medical supervision. If your body mass index, BMI, is below 18.5, if you have experienced significant unintentional weight loss in recent months, or if you have a history of an eating disorder, these protocols are not appropriate without prior medical evaluation. For individuals taking blood pressure medications, fasting can lead to a further reduction in blood pressure. Careful monitoring is necessary. For those on warfarin, dietary changes can impact INR levels. Monitoring should be conducted as you would with any significant dietary modification. For individuals taking lithium, the risk of dehydration during fasting can affect lithium levels, requiring extra attention to fluid intake and physician awareness. Alarm symptoms that warrant seeking medical evaluation rather than continuing with fasting include fainting or near fainting during a fast, significant heart palpitations, inability to eat due to nausea after a fasting period, confusion or disorientation, and any significant unintentional weight loss that is not directly attributable to the FMD protocol itself. Unintentional weight loss that occurs without deliberate intervention is a symptom requiring medical assessment, not a benefit. To conclude, let's return to where we began. A 36% difference in cancer recurrence risk based on when you stop eating overnight. That statistic has remained with me because it suggests that the biological environment we maintain within our bodies day after day through our eating habits, timing, and the fuels we are utilizing at 2 a.m. is not merely a static background element. It is active biology. It's whether autophagy is running or not, whether IGF-1 is elevated or falling, whether immune surveillance is sharp or dulled, and whether cancer-suppressing gene expression is switched on or slowly fading. The research on fasting and cancer is not yet complete. The large-scale prospective randomized controlled trials that would definitively demonstrate that a specific fasting protocol reduces cancer incidence in healthy adults are still being designed and conducted. the National Cancer Institute's funding of 5 studies, specifically on time-restricted eating and cancer, reflects a scientific community that finds this question profoundly compelling and is pursuing it with rigor. What we currently have is mechanistic evidence that is strong and consistent, observational evidence in human populations that is striking, and early-phase clinical evidence that is promising but preliminary. This body of evidence is sufficient for me to state that the interventions I have described, particularly the simple 13-hour overnight fast as a minimum, extending to 16 hours if tolerated, and considering periodic FMD cycles for those with elevated risk factors, have a serious, credible, peer-reviewed evidence base. I believe individuals over 50 deserve to understand this information fully, not as a replacement for essential medical care like colonoscopies, mammograms, and oncological treatment, but as a complement to it. It represents part of the biological maintenance that the evidence increasingly suggests makes a difference in whether the cellular changes of aging evolve into clinical cancer or are caught and cleared before they do. You have more influence over this biology than many have been led to believe. The tools are accessible, the mechanisms are understood well enough to act upon thoughtfully, and the research to refine our understanding is ongoing. If this video has prompted questions you wish to explore further, my next video will focus on the gut microbiome aspect of this picture, specifically examining how the bacteria discussed previously interact with the fasting-driven immune remodeling we covered today. These are not separate systems, they are the same system viewed from different perspectives. Please leave your biggest question or takeaway in the comments section. I read all of them, and they help shape my future research. Keep investigating, and I'll see you in the next one. Dr. Becker.